Physics chapter 26 theory video 4 Faraday's law of electromagnetic induction is what we are going to discuss. Now we know that when a magnetic flux changes with time, we know that electromagnetic induction would occur. So this EMF can be calculated by using Faraday's law of electromagnetic induction. We know that the changes that happens will change the EMF. The EMF is directly proportional to the rate of change of magnetic flux linkage. So that means higher the change, higher the EMF. Then rate of change is obviously we know that it is per unit time. We write it as E equals delta n phi upon delta t. E is directly proportional to delta n phi upon delta t. So that is the n phi is the change in magnetic flux linkage at then delta t is the time. Therefore, this equation gives us magnetic flux linkage change in time, that is given time within a certain period of time. What is the change in the flux, magnetic flux? Then we take the proper constant of proportionality to be equal to 1, and you don't have to know why it is 1. So we have because it is 1, we get the equation E equals delta n phi upon delta t. This is the mathematical equivalent to the Faraday's law. Then this using the Faraday's law, E equals delta n phi upon delta t. Now we know the equation for phi. Phi is phi, we use the equation this BA is flux, magnetic flux, O phi. BA cos theta is the BA magnetic flux if there is an angle in between. So now we are going to discuss how to use this phi along with the n number of turns, that is the flux linkage divided by delta t. So then this value delta n phi divided by delta t gives us the magnitude of the induced EMF, and direction can be obtained by the Lenz's law. We are going to discuss that after this part. So now let's look at this worked example, then you will be able to understand how this is used. A straight wire of length 0.2 meters moves at a steady speed of 3 meters per second at right angles to a magnetic field of flux density 0.1 T. Use Faraday's law to determine the magnitude of the induced EMF across the ends of the wire. Even if they tell you no, even if they don't tell you to use Faraday's law, the only thing that you have to use here is Faraday's law. So now with a single conductor N1, to determine the induced EMF E, we need to find the rate of change of magnetic flux. So we need to find the change in phi, the change in magnetic flux per unit time. So we know that it is the cross section is the straight wire of length 0.2 meters moves at a steady speed of 3 meters per second at right angles to a magnetic field of flux density 0.1 T. So here what happens is, as shown in this diagram, 0.2 wire is moving through this flux density at 3 meters per second. So in a time t, the wire would travel 3t. The equation speed equals distance over time. From that we can figure out what is the distance that it travels. So then we know that it travels 3.0 T. Then we can take the magnetic flux to be B into change in area. Change in magnetic flux is equal to B is 0.10, they have given it. flux density is 0.1. Then change in area is 3 is the 3 is the length into 3t. 3t. Then it gives us 0.060t. I hope you understand how this happens. Then we use the Faraday's law of the law to find the magnitude of the induced EMF. E equals rate of change of magnetic flux linkage, that is N phi upon T. Delta phi, or the change in magnetic flux, is 0.06. We calculated that. Then delta T is equal to T and N equals 1. Then we divide E equals 0.060 T divided by T. Then T to T gets cancelled out. As a result, we get 0.06 volts. Even for whatever the time it is, we calculate the same, we get the same answer. We can use this method to find the magnetic field, the flux density of a magnetic field. Then another situation is given here. A search coil is a flat coil with many turns of very thin insulated wire. A search coil has 2500 turns and cross-sectional area of 1.2 centimeter square. It is placed between the poles of a magnet so that the magnetic flux passes perpendicularly through the plane of the coil. So when you read through these details, you need to remember, or it should come to your mind that what they are asking is for the to use the law or the equation that is given here. So now when you use the Faraday's law into these values that they have given, then you would be able to find the magnitude of the EMF that is given. So in this particular situation, we have to find out whatever the other details that they have not provided using the basic details that they have given. So they have given the number of turns, that means N has been given, A has been given. Then they have given flux density also has been given. B has been given 0.5. Then it is pulled rapidly out of the field in a time of 0.1 seconds. So time is also has been given. So now what we need to do is we need to find N phi. Then we need to understand when the coil is being pulled out from the field, the final flux linking the coil will be 0. The final flux is 0. Because they have given the units in centimeter squared, we have to convert that into meter squared, centimeter squared to meter squared. Then we get the change in N phi is equal to final N phi minus initial N phi. So the final N phi is 0. Then the initial N phi is going to be 2500 multiplied by BA, 1.10 into 10 to the power minus 4 multiplied by 0.5. 1.2 into 10 to the power minus 4 into 0.5. Then after we get this value, we get the final answer to be minus 0.15 Weber. Now we can use the Faraday's law of electromagnetic induction equation and find out the magnitude of EMF. We know the N phi, we know T, then we get 1.5 volts. Even if you have, if you have forgotten, it is the final minus initial N when calculating the delta N phi. If you make a mistake of the negative sign, it actually doesn't really matter, because the final value, we don't get the sign, we generally disregard the sign, right? 1.5 volts. So we have to, what we need to understand is, we assume that the flux linking the coil will fall steadily to 0 during the time interval 0.10. It might not be that. So what we get is actually the average, right? Average of how it falls. I hope you this makes sense. If you don't understand, please let me know. Then I will give you more notes and explanation. But for now, if you have understood, go to the question. But before that, write down the note: Faraday's law of electromagnetic induction. To calculate the EMF when magnetic flux linking a circuit changes, we use this law. Write the equation. E is proportional to delta n phi upon delta t. Leave a line and write the change in the magnetic flux linkage in a time delta t. The constant of proportionality is taken to be 1. Therefore, Faraday's law of electromagnetic induction can be illustrated as follows, and write E equals delta n phi upon delta t. I hope you understood. Please go through question number, the worked examples here, 2 and 3, and try to understand it. If you don't understand it, let me know. Then I will explain it further. If you do understand, please do 10, 11, 12 questions. After that, we will go to the next video.